Alright, so last time we actually did a couple examples with right-hand endpoints and left-hand endpoints. Yeah, we approximated the area under x squared between 1 and 2, I think, using 4 subintervals or something, memory serves. So I sort of just want to go over that, make it more formal, maybe do another example, and then move on from that. So let's actually just get back into that one. We're going to come back to this word under later. So we're going to find out how to do this in general for any number of rectangles, right? So last time we did 4, what if I asked for 5 or 6, something else, right? How do you actually set this up in general, right? So the process, take the interval, and I'm going to label it, right? So I'm going to call these guys by x values, x0 up to xn, right? So it's x0, x1, x2, all the way up to xn. Right? This is, of course, the left endpoint, which is called A. This is, of course, the right endpoint, which is called B. Right? We divide it into n subintervals. Equal length for simplicity, right? In general, they don't have to be equal length, but to make things simple, we're going to make them equal length. Delta x, right? This means, can you do me an equation for delta x? I want to take this guy, having this length, and cut it into n equal parts.
A minus b, b minus a divided by x.
B minus a divided by n, right? You take the length of this divided by n. The length of this, it's a horizontal distance, so it's the right minus left. So this gives you the general equation for delta x, right? Where delta x is just the space between these intervals. Right? They're all delta x. So the first thing you're going to figure out is what your delta x is. How much spacing do you need? Next, figure out a general form for xi, right? For I equals 0 down to all the way up to n, right? So we want to know what are these xi's that we're actually going to use in general. Well, note x0 is just a. How would I get to x1 if I wanted to find this number?
It doesn't. It plus delta x.
You just take a, you add delta x, you get to that number, right? So it's just a plus delta x. And x2?
2 delta.
Right, you start a and now you add 2 delta x, right? Similarly, x3, you start at a, you add 3 delta x's. So in general, how do you figure out the xi term?
no, I minus 1 equals
I delta x. So these are what the forms that your x values will take on. And something like that's going to be really important later. In the finite case, you don't really have to think about it this way, but setting it up this way is going to help us later.
Is that an n or 2?
Come again?
D minus a over
N. Yes, this is n. Okay, so that's your general formula. Now, set up. The area of the ith rectangle will be just f of xi times delta x, right? Because remember, the height of our rectangle was given by the function, and we're evaluating it at these x values, right? So this is the following. So now I'm going to give you the general formulas. If you're using right-hand approximations, then your area is approximately equal to Rn. R just stands for right hand, right? Which is going to be delta x times, right? Now if you're looking at here and you're taking the right hand endpoints, who are the guys you plug into your function? In the first interval, who do you plug in? In the first subinterval, x1, right? In the second subinterval, you plug in x2. You're always plugging in the guy on the right. You'll notice that if you do this until the end, the only guy that gets mixed is the x0, right? So pretty much this guy goes from x1 plus x2 all the way up to the last point, which you can actually write as a summation. I goes from 1 to n f of xi delta x. That gives you the right-hand endpoints. Right-hand approximation. In a similar way, you could use the LNs to approximate this. So it's length times the heights. Now, in the left-hand ones, every guy will be used except the last one, xn. So this one starts at x0 and goes all the way to the very second to last guy, right? Because you can't take the guys on the right-hand side. So this is just the summation. I goes from 0 to n minus 1. That's what xi delta x. Writing the formulas this way is going to make it easier to digest 4.2, but you'll see in practice you don't really have to be this pedantic when you're doing stuff for 4.1. Midpoint approximation. It's just delta x times x1 all the way up to xn. Put a bar here, where xi bar is just the average of the ith term and the term before it over 2, right? This equals the midpoint. Of xi minus 1. We're going to do some examples soon, so this is just an illustration of what I'm talking about here. in the case of using midpoints, I want to look at the interval and use the middle point to get it, right? Now if I know two numbers here, how do I get to the middle point? Well, I just average them, right? x1 plus x0 over 2. This middle point here would be x1 plus x2 plus x1 over 2, etc. So this guy just gives me what I call x1 bar. I don't have to do this formula over and over though, because they will again be at a gap of delta x apart. So all I have to do is find the first guy and then just keep adding delta x to get all the other ones. That would usually be the best way. All right, let's do a concrete example. Oh, this is to emphasize that I'm talking about the midpoint of the intervals here. Putting a bar over something is notation in statistics for the average, the mean. It's because this guy's the average mean. Yeah.
What is the formula of x of what?
This one?
Yeah.
X sub I plus x sub I minus 1 all over 2.
Thank you.
Let's do an example. We're going to do all three, right? So it's very possible in a final they might ask you to do one of these for some given function and some number of rectangles. So a possible problem on a final, for example, would be something like this. They'll ask you one of these, like, do the right hand input, do the left hand input, do the midpoints, right? And this is how you would do that. Okay, so we look at the intervals. Notice that the interval goes from 0 to 6. I know I want to split this into 3 equal parts. This means that delta x is equal to, what's delta x? Huh? Formula. 6 minus 0 over 3. Right? So this is the B, this is the A, and this is the N. Right? N is the number of rectangles or the number of subintervals?
Wait, can you slow down a little bit? Where'd you get the formula?
I wrote it down here. What? I did write it down. I'm using delta x equals b minus a over n. Right? So it's the length of the interval divided into 3 parts. The length is the right one minus the left one divided by the number of parts I want to divide it into. So this means I need to skip by 2 every time, which means that this guy here will be 2, this guy here will be 4, right? Because I'm jumping by 2. So this here is my delta x equals 2. And so on and so forth. Now, the area, if I want to approximate it using 3 rectangles in the right-hand endpoints, how would I do that? Well, this is just delta x times x1 plus f of x2 plus f of x3. Because this guy here is your x0, this is your x1, this is your x2, this is your x3, right? So on the first interval, you take the right one, so that's x1. Second interval, you take the right one, that's x2. Third interval, take the right one, that's x3. So just looking at all the intervals, you're plugging in the numbers on the right side. Delta x I know was 2, and this would be f of 2 plus f of 4 plus f of 6. So this is 2 times, what is f of 2? Well, here's where you go back to your original function, which is y equals f of x. And I just plug in 2. So this is just 6 times 2 minus 2 squared plus, now I do f of 4. 6 times 4 minus 4 squared
Would they ever give us decimals?
This is all for right hand?
This is just right hand.
Would they ever give us decimals? Like something that when you divide it?
No, they'll give you something where you might get fractions, but and they probably won't be too mean, but yeah, it's gonna be have to take some arithmetic. Yeah. So this is gonna be 2. 6 times 2 is 12 minus 4 plus 24 minus 16. This guy's just 0. So this is 2 times 12 minus 4 is 8 plus 8. So that's what? 32. So the area under the curve between 0 and 6 using right-hand endpoints is approximately 32 square units.
That's all we're asking, right?
It's hard to tell. Like here, using the forms that I gave you, you don't need to draw it, but if you were drawing it,
Yeah, when
it would have been this, right? So when you cut this up into 2 parts, here you get over, right? But here, you'd actually get a little bit under. So it's sort of hard to tell for certain.
So it's not like a uniform thing.
No, and here you get 0, right? So it's sort of hard to tell. Right, if it's strictly increasing or decreasing, you can know, but if it's increasing and decreasing, it's not always obvious. So the goal is, I'm just going to take delta x times the sum of a bunch of y values. The y values that I'm taking is the y values that are on the right side of all my intervals. That's basically it. Let's see if we can do it on the left. Huh?
How do you know when to use the right hand?
They'll tell you. They'll say, use right hand.
Yeah, I was gonna ask if there's like some type of notation that'll.
No, they'll use these words.
Alright.
If not, if they don't use those words, they might use a notation like this, but that's unlikely. They'll say R here. This means right hand with 3 rectangles.
That would just be an L.
Yeah, if it's left hand, they'll put an L. If it's midpoint, they put an N. But typically they'll say this: use right hand, use left hand, use midpoint. Right? So they'll tell you what they want you to use, and they'll tell you how many rectangles or subintervals you want. So you'll be given this information.
Wait, so
Yes.
how is f of 2 6 times 2 minus 2 squared?
And plugging it into here.
Oh.
So this just means x equals 2. So plug in 2.
Professor, so that's always the formula for R3?
This is the general form.
Right, the
It will vary with the functions, right? If they give you a different function, you plug into whatever function there is.
That's the general formula.
This is the general formula. You start on x1 and plug in all the x values after x. Right? Pretty much skip the left guy, the first guy, just plug in all the other guys. Right? For left hand, we have the same guy, the same interval.
Start from left.
But now we only pick the guys on the left. So that means 0, 2, and 4 is who we want. Disregard 6 because it's on the right side. Right? So you pick every guy except the last guy. So again, delta x equals 6 minus 0, 3 equals 2. This means that your area is approximately the left hand 3. Just delta x times f of 0 plus f of 2.
But we have to repeat the delta x.
No, but I'm sort of pretending like, you know, I didn't do that.
What's it called? When doing left and right for pretty much for the same product, for the same graph, would one of them definitely be an overestimation and one be an under, or it's just you can't tell either?
In general, you won't be able to tell.
Okay.
You have to draw a graph to see that, right? You have to draw a graph to see
Yeah, if you really want to know, you can put it on graph paper and sketch things exactly.
What about like the scale of minus?
Like this, yeah.
Really?
Yeah, they might ask you like one of these parts, and the final part B would be something else, like what I'm about to do.
Okay.
So this would just be 2 times 0 plus 6 times 2 minus 2 squared plus 6 times 4 minus 4 squared. 2. So this we computed before, that was 8. And this guy was also 8. Right?
It's the same answer.
You actually get the same answer.
Is there any way to check that? Yeah.
Not really.
Okay.
So see, not necessarily is one an underestimate, one's an overestimate. Like symmetry can help you get to a number, right? What's happening here is let's put this into 2, into 4. But we're taking the left hand, so this time the left side, the height is 0. The left side, this is that. And then this is that. So you see the same thing happens, except it happens on the other side, right? This one has symmetry. So the left hand and right hand give you the same thing. Which won't always happen, but it can happen. Okay, how do we do midpoints?
Disregard the left and right.
It means the guys we care about are here, right? In the middle. How would I find the first number? Right, you find the average. You can tell here's 1 because I picked the nice numbers, right? So here you can say the bar is just going to be 2 plus 0 over 2. So you know that this is 1. So the first midpoint is 1. Right? How do we get to the second? Well, you don't have to average again. You just keep adding delta x, right? So you take 1 plus delta x, so you know that this one is supposed to be 3. Then you take 3 plus delta x, you know this one is supposed to be 5.
Wait, you do what?
Find the first midpoint in the first interval by averaging these two. Right, so I know the answer is 1.
Oh,
Right?
well, that's the same formula from here, right? You have 0 prime.
No, that's a different one. That was the one I wrote here. Right, but now you just average the endpoints of the interval to get the guy in the middle. Right, you take the average of two numbers, you get the number exactly in the middle. Right? Once you find the first one, you don't have to do that over and over, you just add the same delta x and it will get to it. This means, in this case, area is approximately equal to m3 delta x times f of 1 6 times 1 minus 1 squared plus 6 times 3 minus 3 squared plus 6 times 5 minus 5 squared. This is 5 plus 18 minus 9 plus 30 minus 25. 5 plus 9 plus 5. That's 2 times 19, which is 38. In this case, the midpoint gave you an even higher estimation. What was happening here? The diagram is not a part of the answer, but I just wanted to illustrate it.
That's something more lower.
Here plug in 2, here plug in 4. Now I take the midpoint. That determines the height of the rectangle. Here I take the midpoint. Height of that rectangle. Take 5. That returns the height of that rectangle. So you see here, we don't have a rectangle that gave us nothing, right? Before, the area under this rectangle was 0. But here, we're actually getting positive areas for all the rectangles. So,
Are we doing some graph for the final?
usually not.
No.
No, usually not. For right hand, you do this. For left hand, you do this, and for midpoint, you do that.
Show your work on time.
Yes, I'd expect you to write out from here down. I guess you can do this if it helps you just set things up. Just sketch out the interval and write the numbers on it. And then stuff.
Wait, you verify.
Yes.
We can have trigonometry functions in this.
Your f can be anything.
No, I thought.
Wait, so our own professional
Also
radar.
fine, right?
Yep.
That doesn't make sense.
Huh?
That doesn't make sense.
I don't know.
Yeah, this isn't that crazy. I mean, if you go through the homework problems, you should get it by the end of the yeah. All right, so now let's talk about finding the exact area. So what if the approximation isn't good enough? Right? We spoke about this last time, how we got the exact area. How did we get the exact area?
Each little square.
What did we do?
Actually, those answers.
Conceptually, right? You're approximating with rectangles. Infinite number. Let n approach infinity. That's how we're going to get to the exact area. So A is actually equal to, take the limit as n approaches infinity of our n, which is actually equal to, when you're taking an infinite number, it actually won't matter which set of the two. Take this one, right? And again, it is actually possible for them to do this one, but this is actually a lot harder than that. And especially if the function is mean, it's going to be really nasty. But, so let's do, so illustrate. They'll all be the same one, so I can just pick, let's do it with our n. We have delta x equals b minus a over n, right? And this time we don't know what n is. And we know that xi is equal to a plus I delta x. This means the area is exactly equal to, if I let n goes to infinity, of this summation. That was the shorthand for the right hand, right? So I'm taking all x1, x2, x3, x4, x5, blah, 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 all the way up to n, and then I'm letting n go to infinity. So I'm taking an infinite sum. Which, by the way, all I have to do, xi, just plug in the formula. It's just a plus I delta x. And we know that delta x is just b minus a over n. And this will give you area. Not an approximation of the area, the exact area. Because you're taking an infinite number of rectangles, you're filling in all the little gaps that you missed by using a finite number of rectangles. So let's see this in action. It's something that's probably familiar. Using Riemann sums is going to be the hint that this is what they want you to do, right? If they just ask you to find the area under a curve, this is not what you would do. This is really bad, right? Because it gets tedious as you see, especially if you can imagine if we have an ugly function there, it'll take forever, right? But if they say using Riemann sums, you have to do it this way. So this is what they expect you to do. Let's do an example.
So these are the elements.
Yes, using Riemann sums, find the exact area. It means you're going to have to do this one. So here, what's your delta x?
Where our delta x is 1.
Huh?
1 flat. I mean, no. What's our x? So 1 minus 0 divided by how many times?
b minus a over n, right?
Is it
Which is 1 minus 0 over n, right? So delta x is just 1 over n.
Oh, I thought n was infinity, right?
No, n is n. N can be any number, but we're going to let it approach infinity at
Yeah, so
at the last one.
approaching.
So n is just n. That's our delta x. How do we find the xi's?
X of I would be the 1 of the sum.
It's a plus I delta x, right? What is a? A is 0 plus I times what is delta x?
1 over n.
1 over n, right? So this is just I over n, right? So what is f of xi?
What's x of I? Yeah. I x
Just this squared. That's the formula. I over n squared. This means the area is exactly equal to the limit as n approaches infinity. Sum of I goes from 1 up to n of I over n squared. Right? This is the f of xi times your delta x, which we know is what? 1 over n. Does that look familiar?
Yes.
That was a bonus problem on the test, right? I asked you to compute this. What I was actually asking you to compute was the area under x squared between 0 and 1. What was the answer? Who actually attempted that? Did anyone get to that point? Yeah? Okay, how did you do it?
Find the exact areas of any.
Well, I'd start by
So I
simplifying.
was using simple integration to do that. There we are.
Find the exact area.
I mean,
I'd simplify, right? This I can write as I squared over n squared times 1 over n, right?
I use it.
This is just I squared over n cubed. In this expression, what's our variable? I is the variable, right? Remember we did this, the sum, the index tells you the variables. Which means n, as far as this summation is concerned, is a constant. I can just factor it out. And what is this guy?
The formula which we learned.
We learned the formula for that guy.
n plus 1 and 2n plus 1 over 6.
So this is actually equal to limit as n approaches infinity of 1 over n cubed times n plus 1, 2n plus 1, all over 6. What's that limit? Going back to chapter 1.
It's 0.
No, it's not 0.
What?
Oh, that's
Wait. Is it a third?
It's 2 over 6, which is 1/3. Third is the answer. The exact area under the curve x squared between 0 and 1 is 1/3 square units. The idea is you have to realize that this was actually 1 over n cubed times, this would be 2n cubed plus blah blah blah. The blah 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 doesn't matter because we're going to infinity. Look at the highest powers. The highest powers are the same, right? What does that mean? It goes to the ratio of the coefficients, right? The coefficient of this guy is 6, the coefficient of that guy is 2, so it goes to 2 over 6.
question. How did you get
1
over n, like 1 minus 0?
This? Yeah, this is the A, right? And this is the B. B is always the right hand endpoint. A is the left hand endpoint. So it's this minus this over n.
I missed that part.
So typically on a final, what they could do is they could give you a function and then say, use right-hand endpoints with 3 subintervals to compute this. And then they're going to say, use Riemann sum to find the exact area. So they're going to ask you to approximate it in like part A, and then part B, they expect you to actually find the exact one, which is you do this.
So what do you call the other one? Right hand sum? Left hand sum, midpoint sum?
Yeah, they could ask you right-hand, left-hand, or midpoint.
Well, they're all the same? They're all the same?
No, we did the.
Oh, wait.
Why did you factor out the 1 over n?
Well, I didn't have to. I just did it so that I could see this, because I know what that is. Right? I have to n of a squared. We did a formula for that.
We found the exact area under the curve with the right hand, left hand.
No, you just use this formula here that I did.
Alright, so you know that doesn't
Technically, it's set up in terms of right hand, but it doesn't matter.
Alright.
What you pick, actually.
Question is like, you said n is constant, right?
According to the sum, n is constant.
How do you know? Like, the n
Because
is
the variable is the index. I is the variable. Right? The letter down here is the variable. Which means anyone else, any other factor, I can factor it out. Right? Because we did that property, we could take constants out. And that leaves me with this, which I have a formula for, so I just plugged it in, and then I actually took the limit. Yes? Any questions on that?
So we don't have any formula for 1 or 2. Like we have a formula for I squared.
No, 1 over n cubed is 1 over n cubed. What do you mean? You don't need a formula for it.
So it just stays like that.
Yeah.
Now you got 1 plus 3 you
The highest powers were the same in the top and bottom, so it goes to the ratio of coefficients. We did that in chapter 1.
what? No.
You're the camera person. Okay, so that actually is 4.1. We're done with 4.1. Buy another notebook. That's not worth It's gonna be worth it.
Notebooks won't see you anymore.
I'm not looking at the money spawn, it's like
So, alright, in 4.2, we're not doing a lot of examples. It's mostly what I want to get from 4.2 is the conceptual stuff. So, I'm just going to be writing down a bunch of stuff and talking about it, basically.
Are we gonna do example?
I feel like I learned better if you showed me just how to solve this instead of explaining me all this. Because when you play all that stuff in the book, it's like, when you show me the example how to apply it, it's like, oh, okay.
Well, these concepts are actually important to
Alright.
learn. Because when we get to 4.4, we're going to be applying this in the background. When you're actually doing an example, you have to be thinking about this stuff. So it's actually important that I do this. It's called a definite integer. Definition.
What do we do?
Yes, that formula we have for the exact area, I'm going to call it this guy very suggestively. This is called the definite integral, right? This is the notation for it, that is the formula, right? Where delta x and xi are defined as in 4.1. Of course, this limit doesn't have to exist, but as long as it does exist, we call it the integral. When the limit exists, we say f is integral on b. That is what we say. Integral.
Integrate.
No, integral. Yes, very integral. So
That's not fast.
that's just some terminology. If you see something like this, if I say the integrand, I'm talking about just the function, right? A and B are called the limits of integration. A is called the lower limit, B is called the upper limit. So very soon I'm going to be talking about integration, and I'm going to be saying all these terms. You need to know what I'm talking about. So that is what they're called. Okay, some important things to note. X is a so-called dummy variable, right? The variable does not change the answer. That is, say the integral from a to b of f of x dx. It's exactly the same if I phrase it as the integral of f of y dy. It's exactly the same as if I phrased it as the integral of f of p dp. Really, the variable I'm using doesn't matter. You're going to get the same answer all the time, etc. This is a very important concept. It's going to be important when we cover substitution, which is 4.5. This is basically the rule that's going to tell you the substitution u equals x is never a good substitution to make. You change the u to an x or the x to a u, it makes no difference in your life whatsoever. Right? So sometimes I'm there in the tutoring center and I say, oh, you have to do this integral using substitution. And the student, what's substitution? U equals x? It means they do not know what is going on. Changing the name of the variable makes absolutely no difference whatsoever. It does not make your life any easier, it just looks different. So that's something important. Something else that's important. This is actually very important. If we switch A and B, then delta x becomes negative. And so, integral from A to B, delta of x dx. Remember, this is the summation of something times delta x. But if I switch A and B, the delta x becomes negative. So it means that if I switch the limits on an integral, the result is the negative of the original integral. This is actually a very, very important thing. Right. So I have this integral, and I switch the numbers, I have to put a negative sign here. Also, if A is actually equal to B, then delta x is actually equal to 0, so I'm just adding 0 over and over. So this implies something else that's very important. If the upper and lower limit are the same thing, the answer is 0. It doesn't matter what this function looks like. Function can be anything. And I will always get 0. Put that in a box, because this is very important. Right? So if you swap the numbers, you get the negative of the original answer. If you go between a number and itself, you get 0, right? What else do we really need to know? Yes, the idea of negative area.
So this produces delta x?
Huh?
This produces delta x?
No, delta x is b minus a over n.
Alright.
If you switch b and a, you just get the negative of the original. So then this gets negative. And if b equals a, you get 0 on top. So the answer is 0. What else? Yes.
Are we not going to revolution?
No, that's called 2.
The what?
He's asking about volume of revolution.
Oh God, don't go.
Oh, yeah.
So this is just saying if we're taking, if we start to do a Riemann sum, right, on A, B, and there's some interval where our function is negative, then over here our rectangles would go here and we'll just be taking the y value times delta x, we'll get positive areas. However, when we're down here, now our y values are all negative. We'll be taking negative values, right? So we'll actually get the negative areas of these rectangles, right? Right, so these will all give us positive area. This will technically give us what? Negative area, right? Whatever the area is, it will be negative because the y values are negative. This implies so let's say in theory I actually knew what the area here was, like this. I knew it was some area, called it A1. This, I knew it had area A2. This, I knew it had area A3. Then, the antiderivative is just going to be A1 plus A2. According to our formula, we'd actually get the negative of the area here. So wherever your function is negative, you get negative area, right? This implies a very important concept regarding the integral and what it does. What this guy actually means, how we can interpret it, is just as an area, in particular the net area under a curve, right? It's going to be all the areas above the horizontal, we get positive areas. The areas below the horizontal, we get negative areas. And then we add up all these areas, and that will actually give us the result of this guy. Right? So if we somehow know these areas individually, we can figure out what this integral is without even doing any work. Just add up all the areas. That is a very important concept. Another important concept is we can break limits up. Over intervals. So this will come in handy in 4.4 and 4.5. So, example. This is my f of x, this is a, this is b. Let's say I have some random numbers in here, c and d. Right? Then the area under this guy is the same as the area between these two plus the area between those two plus the area between those two. Right? I can actually break the limit into a bubble. This means integral between a and b of f of x dx is equal to, I can go from a up to c of f of x dx plus I can go from c up to b of f of x dx. Right? And it doesn't matter how the numbers are arranged, I can actually split them up. So I can throw a number between any two limits and just add the integrals and it'll be fine.
Can you explain that again?
Wait, let me write down some. I can go from A to C, then go from C to D, then go from D to B, what I'm saying is we can break up this interval into chunks. And I can integrate on each chunk and add them together. And it's the same as integrating the whole thing all at once. So I can break, so here what I did was I took A and B and I broke it up into two parts, A and C, and then C and D. And I can do that and add them and it will be the same. Right? Or I can break it up into A and C, C and D, and D and B, and I get the same thing. This is, we'll use this in the fundamental theorem of calculus to compute some problems, but it's also really important when we're doing piecewise functions, right? Sometimes your f on this interval is defined differently from your f on that interval, from your f on that interval. If that happens, don't freak out, just break it up into different intervals and compute each one separately. So that is a super important concept. We're going to be using that option. I can go back to that example here. We're eventually going to use all this, but it's important that you know that you can do them. They'll actually make computations easier later on. So if I call this A, and I know this intersection here is C, I know that intersection is D, this is B, then again, integral from A to B, the left of x dx is equal to with the C, left of x dx, plus C to D, left of x dx, plus D up to B, left of x dx. Now this integral just tells us the area under the curve, the net area between A and C, that's just A1. Plus, this tells us the net area under the curve, in quotations, between C and D, because our function is underneath the horizontal, this will give us the negative area. Plus, this gives us the net area between D and B, so this is just that area, right? Which is, gives us the same thing as before. So the integral, we can really think of it as computing areas. We can break up different areas and compute integrals on different parts. And so it allows us to do all this stuff. No, just a list of properties in it.
It's 6:50.
Just a list, I don't want to push this all the next. Properties. Assume. Integrate a constant on an interval, it's just a constant times the length of the interval. You guys be quiet so we can finish.
What is that?
You can integrate a sum of functions by breaking them up and integrating each function separately. Right? And this is because we can break up summation signs. We know really the integral is just a summation and taking the limit. And summations distribute across sums and the limits do as well, so integrals do as well. The integral from A to B of a constant times a function is just a constant times the integral of a function. We can factor constants out. And that's because we can do this for sums and limits, so it will work here. Or, if your function is positive on an interval, then the integral will be positive on the interval. integral respects order. And that's it for 4.2.
You guys better
No,
remember
but
to get it all the time.
Yes, 4.1
Are
and
you
2 are due
serious?
on Thursday.
Like half the class left on, so the
We didn't do
Yeah, but on
the
video.
examples.
We know
You don't need exams.
What do you mean?
it didn't
Don't
count
need
until
exam.
How
like
are
3
their,
minutes.
how's their homework?
Trust me, do the homework, and if you read this carefully, you'll be able to do it.
Guys, it's